We present Speech-Augmented vision for exploratory data analysis. In the last few years, thanks to low-cost VR HMD, several VR offices became available. This application allowed the display of standard 2D documents on VR screen, where multiple users can collaborate while embodied in avatars. Inspired by these applications and by previous research focusing on immersive VR environment for collaborative analysis of 2D data, we developed a virtual reality environment with a series of 4 screens organized in a cylindrical layout, where users can observe 2D data while being embodied in avatars. The purpose of such environment is to explore visualization techniques to enhance mutual awareness of visual attention, which is an essential part of collaboration. The ability to identify collaborators' visual attention is therefore crucial for successful collaboration. As such, previous studies have explored field of view and eye tracking-based visual cues. Although these visual attention cues offer improvements for mutual awareness, they have limitations. For example, pointer-based visualization based on gaze input can be distracting or confusing due to calibration issues or to natural-looking behavior, while field of view-based visualization only provide an estimate of visual attention. Additionally, both pointer-based and FOV visualization do not afford the dynamic visual representation of different types of attention, such as focus and distributed attention. We propose Speech-Augmented vision, a novel visual attention cue which depicts the general direction of the head but can dynamically focus on the elements named by participant during natural verbal communication. Such technique leverages speech-to-text AI model and can be used in VR headsets that lacks eye tracking. We compare our proposed visualization with a field of view visualization. Cone vision is a technique which uses previously collected gaze data and captures the area consisting of 70% of gaze fixation. The resulting visual cue is then generated by intersecting the cone that has the vertex in the center of the head with the VR screen, as well as we compare it with pointer-based visualization driven by eye gaze. The eye gaze cursor condition displays a graphical cursor at the gaze location on the VR screen. The position is calculated by intersecting the raw gaze direction with the VR screen. We evaluate our novel technique in the context of exploratory data analysis, asking participants to extract insights from 3 different datasets about Hollywood movies, gender bias in Hollywood movies, and car risk insurance rating. Before the experiment, we provide participants with examples of valid insights. We design a 3x3 within participant experiment where we manipulate the 3 levels of the visual cue in combination with the 3 levels of the dataset. In each experiment trial, we measure head, eyes, and hand behavior, as well as we recorded verbal communication and a video of the experiment from a monitoring application. In order to evaluate the experiment condition, we look at how region versus pointer-based cues affect joint and individual visual attention. We process joint gaze behavior to understand the impact that the different cues have on mutual awareness. We also process individual gaze behavior to understand if it is affected by the different cues. We find that region-based cues support mutual awareness equally well or better than pointer-based visualization and concentrate gaze within the depicted region. To evaluate our proposed method, we analyze the transcribed verbal communication to classify the different types and frequencies of verbal references to the data, with the aim of understanding how often participants explicitly name labels versus how often they use other types of verbal references. And finally, we look at how well our proposed method of head direction and speech can approximate eye gaze when compared to head direction alone. Results highlight that the most frequent verbal reference is based on explicitly naming visualized labels and that capturing this information improves gaze approximation over head gaze of about 50 pixels. We process joint gaze behavior to quantify the amount of time participants spent concurrently looking at the same area of interest. We did so for 2 granularity levels, the graph and the page. We performed a one-way repeated measure ANOVA for each granularity level. Result shows a statistically significant difference with a non-trivial effect size that shows that participants spend 10% more time gazing at the same page on the COV condition if compared to the eye cursor condition. The region-based visualization we used is based on a previous dataset. Its contour represents 70% probability of user fixations. To understand how the displayed contour affects user case behavior, we calculate the percentage of case samples that are within it in each condition. In the depiction, you can see how the individual case behavior changes across the three conditions: COV, speech-augmented cone of vision, and the eye gaze cursor. By inspecting the images, it's clear that contour-based visual cues alter individual visual attention significantly by focusing it within the depicted visual cone, showing an increment of 20% if compared to a condition in which the contour is not displayed. Therefore, the region visualized acts as a container. Furthermore, we run a repeated measure ANOVA, which show an increment of 20% if compared to a condition in which the contour is not displayed. Therefore, the region visualization acts as a container. Such result is interesting as shows how much the gaze diverges from the head's direction, therefore how well the head direction approximates the gaze, and such effect could be leveraged by head-based interaction techniques. We perform a classification aiming to quantify the type of verbal references used to negotiate the shared context of visual attention, as well as to quantify how effective is our proposed method in capturing them. We are interested in understanding if participants verbally refer elements by directly naming their label, therefore producing a valid input for our system, or if they use a different verbal reference and therefore producing a reference that our system could not capture. For example, a participant could ask to move the shared focus of the analysis to a different graph from the one the pair is currently working on by explicitly naming the graph title. In this case, our system can capture such event. Otherwise, a participant could ask to move to a different graph by saying, let's move to the next graph, therefore relying on the left-right ordering convention and avoiding to mention the explicit label. In this case, our system would not be able to capture such event. This classification helps us to understand if our proposed method captures more verbal references than it loses. We perform an ANOVA analysis that shows a statistically significant difference between verbal references based on explicit labels and all other verbal references types. Participants used labels as a mean of verbal references about 25 times more on average than all other types of verbal references identified. This classification also helps us to understand if our proposed method affects verbal communication. As results show no statistical difference across conditions, we can rule this out. Moreover, we look at how many references participants perform in relation to the target granularity. Results showed significant differences across all granularity levels, indicating that participants refer more often to smaller targets than to larger ones. However, they show no differences across conditions. Therefore, our proposed method does not affect verbal communication. To evaluate if speech is a valid input for a visual attention method, we look at its contribution towards gaze approximation. To approximate the gaze, we look at the transcribed verbal communication and pick the last 2 grams. We then run a similarity matrix named RuGel for each of the displayed labels. We use the resulting root mean square error values to run a repeated measure ANOVA to see if there is any differences between the methods in the conditions. This difference highlights how our method outperforms the head gaze as an approximation of eye gaze in the eye tracking condition. An interesting insight is that this difference is only present in the eye tracking condition where the COV is not present. In the COV and COV plus speech condition, the presence of the contours keeps the vision closer to the head gaze, therefore hindering the eye gaze from spreading wider. Contour-based visualization perform equally well, if not better, than pointer-based visualization in fostering mutual awareness of visual attention during collaborative work. Furthermore, contour-based visual attention cues significantly alter individual visual attention by focusing it within the depicted regions. Participants utter keywords present in the visualization as the primary way to perform verbal references in all experimental conditions. Our result shows that when the COV is not present, speech improves the accuracy of the head gaze by about 50 pixels on average. We released the first collaborative dataset of head gaze, hands, and the transcribed verbal behavior, which can be downloaded from GitHub. Many thanks for your attention, and I look forward to answering your questions.